Today we're going to talk about a very unique concept called the limit of a function, and it's kind of a really different idea, a really different type of math that than you're used to. So we're going to talk about it a little bit here, just to kind of give you an introduction. And we'll start off by looking at the graph of x squared minus x plus 2. There's our function, and it's your standard parabola. And what we're going to do is we want to find values of f of x when x is very close but not equal to the value 2. So here's what I mean by that. I have my table of values here, and I have 1.9, and then I increase a little bit each time up to 1.999. I'm not quite at 2 yet, but for each of these values, I have a slightly different y value. And if you look at them, they're increasing and increasing and increasing to where it looks like as x is practically 2, y is practically 4. So this is a numerical example when you look at the table of values. Now graphically, we can see the same thing. As I approach x, along here, my y value is approaching a value of 4. So I don't have to be at 2, I just have to be near 2. When my x value is near 2, my y value is near 4. So that, believe it or not, is the concept that we're going to talk about today. When x, and I can say it in words, when x is close to 2, f of x is close to 4. So as x approaches 2, f of x approaches 4. And we say it approaches a limit of 4. So to write that information in limit notation, here's what we do. We have LIM, that stands for the limit. The limit as x approaches 2, so we have our arrow, it's not a very good looking arrow, but as x approaches 2 of my function that's equal to 4. So again, that says the limit of f of x as x approaches 2 is equal to 4. That's how we do that. The general definition of a limit, I just give it to you here, and you can write it on your paper. A limit is the value of a function. The value a function is approaching as x approaches a certain value. So it's different than the actual value itself, and that's kind of the goofy concept that we have to understand, that the limit looks at where is the function going, and it doesn't really matter where it ends up at that point. So that's what we're going to look at with some examples coming up. But before we get there, it's real important that the existence of a limit, the existence of a limit never depends on the value of the function. Never depends on the actual value of the function. And let's say the existence of a limit, let's say I need to put something in here, as x approaches a value c, never depends on the value of the function at x equals c. The existence of a limit as x approaches a certain number never depends on the value of the function at that number. So I'm going to demonstrate this with 3 examples, and then in class we will look at evaluating limits graphically and numerically. So we're going to look at 3 cases. The first case is the fact that f of x is a continuous function. So here we have our standard linear function. F of x is equal to x plus 1. It's a line. It is everywhere continuous. There are no vertical asymptotes. There are no holes, nothing. So when you look at this guy, as x approaches 1, so let's say my x value is approaching 1, well, we have to look at what my y value is approaching. As x approaches 1, my y value is approaching 2. Okay, as I follow along on the graph, it's heading up to a value of 2. So that's what we say. As x approaches 1, f of x is approaching 2. So as a limit, we can say the limit as x approaches a value of 1 of f of x is 2. Now what's the value of the function when x is at 1? That we write like this. F of 1 happens to also equal 2. It's a continuous function, so the limit is actually equal to the value of the function. But again, in the end, that doesn't really matter. So I'm going to show you that in the next example. All right, so here we have a function, g of x is x squared minus 1 over x minus 1. So this function is actually undefined when x is 1, because if we substitute a 1 in for x, we're going to get a 0 in the denominator, and that's not going to work for us. But everywhere else it's continuous. So we're going to evaluate this at the same place. As x approaches 1, as x approaches 1, I don't have an answer. I don't have a value for f of x. However, that does not matter, because as x approaches 1, if I follow the function, it looks like it's headed towards 2. Okay? Either way I go, as I follow this function, it is approaching 2. If you were to evaluate this function for numbers really close to 1, you would see in your calculator that the y value is going to approach 2. So that's what we write. G of x approaches 2. It doesn't get there, because at 2 it's undefined, but it does approach that. So the limit as x approaches 1 of g of x is equal to 2, even though g of 1 is undefined. That's okay, because the limit of a function does not depend on the value of the function at that point. Finally, we have a function that is defined at 1, but with a different value. This is a piecewise function, so it looks like g of x. Looks like g of x for everywhere where x is not equal to 1. But when we have that discontinuity, we define a different value. So we do have a value for h of x when x is equal to 1. And here's what the graph looks like. We have this is called a whole discontinuity again, and the value is actually down here, and then it keeps going. So when we look at my function as x approaches 1, we're looking at two different things here. When we want to see the limit, we still follow along and look at where the function is approaching. So when you're following along here, my function is still approaching a value of 2, even though it's not defined there. So the limit is still what is happening really close. When x is really close to a value of 1, where is my function heading? And in this case, the function is heading to a value of 2. So as x approaches 1, h of x is still approaching 2. The limit as x approaches 1 of h of x is equal to 2, even though when I find h of 1, when I want to evaluate the function, when x is 1, it's wherever the solid dot is. When x is 1, h of x is 1. So h of 1 is equal to 1. The limit doesn't have anything to do with the value of the function at that point. So here you have three different cases, three slightly different functions, and they all have the same limit because they are all behaving the same way as you get close to the value. It doesn't matter what happens right at the value, only as you get close. So in class we will look at this graphically and numerically and do the examples in your notes.